So in this lab, I wanted to investigate the motion of a ball of yarn that moved at the same speed without changing direction. By knowing a few things about my system, such as the velocity, the time, and the mass, I'm able to predict a few things about my system. Using Newton's second law of motion, I'm able to know the quantity of the total forces from the surroundings on my system. I'm also able to predict the final velocity of my ball of yarn when I know the yarn's final position and the final time before it rolls off my desk. I will first talk about my experimental observations, then discuss the theory that was relevant to these observations. I'll then go over my computational model and the assumptions that are inherent in it. Afterwards, I'll analyze the comparisons between the two and see how well my data fits the model. So the results I obtained were two models, one with an assumption of zero net forces, which does not accurately predict my observations, and another model that does account for the initial force vector, which is a much more accurate model. So I'm going to explore the constant velocity of this yarn with the help of Newton's second law of motion. Assuming that there are no net forces, which means that my calculation is only considering the change in time as it relates to the change in velocity. The system mass does not matter since it's related to the force, so if the force is zero, that multiplies with the mass and it drops out. Also, I only know the mass. It's a scalar with SI units of kilograms. And I'm also assuming that it is unidirectional, this motion. So let's compare the theory with my experimental observations. So Newton's second law states that the change of momentum of a system is equal to the net force acting on the system, multiplied by the duration of the interaction. The time interval, delta t, must be small enough that the net force is nearly consistent during this time interval. So really, it is all about the ratios. The ratio of the change of velocity, or Vf minus Vi, over the change of time, delta t, is equal to the net forces divided by the mass. So this equation is telling us a few things. If we were to graph this, we would see that velocity is our graphed function, time is our independent x variable, and position is a function of time, so it is our dependent y variable. Since it is assumed this motion is constant without any forces, it should be a straight line like demonstrated in this example position graph in the bottom right. As for my computational model, I made use of while loops to iterate Newton's second law of motion equation in steps of 0.01 for 1.1 steps. This means that during each loop step, a calculation of the final velocity for that step is calculated. I gathered these 110 calculations and made a line chart of this velocity. I had some choices for my parameters. The ball's mass I made to be 0.1 kilograms or 100 grams. The position of the ball is the x position that was in my tracker analyze video. This value means that the objects start on the positive 5.9 x-axis in the first quadrant. My velocity was moving in the negative direction to the left along the x-axis. It's denoted by the negative 4.7. This is in meters per second since it is a function of time in seconds and position in meters. This value was calculated by taking the first of tracker's position values and subtracting it from the last position value and then dividing that number by the change in time. Changing the sign of velocity denotes which direction the object is moving along the x-axis, and if I were to increase this value, the object would move faster, likewise moving slower if I decremented the value. So what do we get when we have these parameters? So it seems that our model does not predict the motion of my objects. So let's see if we had changed our axes. What would happen? I chose x as my horizontal and y as my vertical, so the ball of yarn travels in the negative x direction, with the origin being the center of the ball. If I was to normalize my coordinate vector, my unit vector would be a negative I hat, positive in the right direction, negative towards the left. Changing the axes would not have affected my final velocity calculation. It just would have been another way of visualizing my data, since if I flipped the axis 90 degrees, my object would be traveling vertically, not horizontally. If I flipped it 180 degrees, my object's initial position would be negative, and it would be traveling to the right in the positive direction. Once again, it doesn't affect my values or the magnitude, it just affects the direction. So if I wanted a better model, flipping the axes would not be the better choice. But what about my forces? So this computational model does not predict the motion of the object observed. This is largely due to the fact that I declared my force to be zero in my model, which in my experiment it was zero. In Newton's second law, we are concerned with the net or total forces. There are, of course, net forces from the surroundings affecting our object. Usually we can't determine this just by observing our object, but we are able to calculate it knowing our velocity and time, which revealed through the ratios. So I can take my model data, find the final time, subtract the initial time from it, then find my change in velocity, divide the change of velocity by the change of time, and multiply it by our mass of 0.1 kilograms to get a net force of about negative 0.5 newtons. So this is what it would be like. And this results in a graph, and my experimental data fits pretty well. It is no longer having constant velocity, but with a rate of change that is no longer constant, so that is why you see the curve. So in this lab, I learned how to make motion predictions. I was able to predict the forces acting on my system and predict the final velocity my ball of yarn was traveling at. These predictions were calculated using computational tools, using a loop to iteratively calculate repeated applications of Newton's second law using delta t.